Thermal conductivity of various materials. Hydrogen, helium, air, carbon dioxide, all these gases. Next one is the insulators, fibers, wood and foams. Next one, liquids, mercury, water and oils. Then non-metallic solids, oxides, rock, food, rubber. Then metallic alloys, aluminum alloys, bronze, steel, nichrome. Pure metals, silver, copper, iron, manganese. And the last one is non-metallic crystals, diamond, graphite, silicon, carbide, beryllium, oxide and quartz. Thermal conductivity of gases is proportional to the square root of the absolute temperature T and the inversely proportional to the square root of molar mass m. Like gases, the conductivity of liquids decreases with increasing molar mass. Liquid metals such as mercury and sodium have high temperature, high thermal conductivities and are very suitable for use in applications where a high heat transfer rate to a liquid is desired, as in nuclear power plants. In solids, heat conduction is due to two effects. The lattice vibrational waves, the free flow of electrons in the solid. The relatively high thermal conductivities of pure metals are primarily due to the electronic component. The lattice component of thermal conductivity strongly depends on the way the molecules are arranged. For example, diamond, which is a highly ordered crystalline solid, has the highest known thermal conductivity at room temperature. For gas, molecular collisions and molecular diffusions exist. See here the picture. For liquid, molecular diffusions and molecular collisions also exist. And the last one, for solid, there is the electrons. Lattice vibrations and flow of free electrons can happen in the solid phase. Thermal conductivity of gases gradually increases with temperature. Unlike gases, the conductivity of liquids decreases with increasing temperature except water, that firstly increases with temperature and then decreases. In solids, the conductivity of solids decreases with increasing temperature. Some solids show tremendous rise in conductivity at very low temperature. For example, Cu, that means copper. And there is a figure where things get clear for you. Next topic, thermal diffusivity. The product rho Cp, rho being density kg per meter cube and Cp is the specific heat joule per kg Celsius, is called the heat capacity of a material in unit volume basis joule per meter cube Celsius. Thermal diffusivity, which represents how fast heat diffuses through a material and is defined as alpha is equal to heat conducted divided by heat stored. That means K divided by rho Cp, which unit is meter square per second. Thermal conductivity K represents how well a material conduct heats and the heat capacity. Rho Cp represents how much energy a material stores per unit volume. The thermal diffusivity of a material can be viewed as the ratio of the heat conducted through the material to the heat stored per unit volume. A material that has a high thermal conductivity or a low heat capacity will obviously have a large thermal diffusivity. The larger the thermal diffusivity, the faster the propagation of heat into the medium. A small value of thermal diffusivity means that heat is mostly absorbed by the material and a small amount of heat will be conducted further. Let us consider sudden release of heat from a point source. See here, this is heat diffusion, this is also heat diffusion, and this is also heat diffusion, but all these three pictures are not same, they have different. Heat will propagate in all directions from a point just after being released. It is similar to growing up of a sphere. With time, heat will propagate, forming an imaginary sphere getting bigger and bigger. The propagation rate is related to the rate of increase of the sphere surface area, and hence any propagation parameter in three-dimensional has the unit of meter square per second. Thermodynamics and heat transfer. There are the differences between thermodynamics and heat transfer. Thermodynamics concerned with the amount of heat transfer as the system undergoes a process from one equilibrium state to another. Heat transfer deals with the determination of the rates of such energy transfers is the heat transfer. Thermodynamics deals with the amount of energy in form of heat or work during a process and only considers the start and end states in equilibrium, no tension about time. Heat transfer deals with the rate of energy transfer, thus it gives idea of how long a heat transfer will occur. Thermodynamics deals with the equilibrium phenomena. Heat transfer deals with time and non-equilibrium phenomena. Heat can only transfer when there is a temperature gradient exists in a body, and which is indication of non-equilibrium phenomena. In short, thermodynamics gives why a process will occur, and heat transfer will tell how a process will occur when there is a concern about transfer of heat.